Okay, so you have spent last week learning the basics of intersection theory as given in Fulton, roughly the first 5 chapters. So the goal of this mini series of 4 lectures is to construct the intersection product. We will see the definition today from the Fulton-Macpherson theory, which is worked out in Fulton's book. But we are also going to see some classical, how things developed classically and how intersection product was thought about, let's say 50 years ago, when Serre gave his famous Store formula. Okay, so what's the general goal of intersection theory? Is to construct a ring structure on. So I'm going to, this abelian group you have studied last week. So A upper star X, I'm using grading by codimension. That's for the reasons of functoriality. The functoriality is usually by pullback, and there the upper grading, the codimension grading is preserved, not the dimension. That's why. But anyway, so of course we will require X to be sufficiently nice. So for smooth X over a field. Okay, so what do we want to do? So we know that the Chow groups are generated by classes of closed subvarieties, right? So what we need in particular is, if we are given 2 closed subvarieties, then to these we would like to associate the intersection product, which we will denote by V dot W, so this should be kind of supported on the intersection of V and W, and should be very closely related to the geometry of how V intersection W, V and W are situated inside X. Okay, so the classical approach, in fact, started from the works of Severi in 1930s. So it's a very old subject. So what is the first? Yes, so I will come to this because I have to talk about proper intersections and so on. So ideally, this should be inside so this should have dimension equal to the dimension of V plus dimension of W minus dimension of X. If we so we will define it in Z, and then but for nice things to happen, we will require it to factor through rational equivalence, and that is one of the main things that we have to address. It's one of the main tricky or technical or controversial points. So which is the classical theorem that you know which deals with intersections? Bezout's theorem. Okay, and what does it say? If 2 curves inside P2 don't have a common component, then the number of points counted properly with multiplicities is equal to the product of the D. Yes. So not having a common component is an important condition, and in general this is going to be replaced by they should intersect properly, and we will describe what that means. So basically, so here's what we want to do. So if V and W intersect properly, and I will define this in a minute. Okay, so then and if so of course, V intersection W has no reason to be irreducible, right? So if you can decompose this into irreducible, so if this is an irreducible decomposition, this is a decomposition into irreducible components. So then the idea is that we should have, so this as a cycle, as an element of Z, should be given as a linear combination of these Zi's. right? And then the whole problem is about determining what these numbers are. These are called intersection multiplicities of, so this is called the intersection multiplicity of V and W inside X at Zi. So it depends upon four things. It depends upon X, it depends upon V, it depends upon W, and it depends upon Zi. Okay, so this is what we want to, yeah, so I have not defined this, so then we should have something like this. And so then, motivated by Bezout's theorem, Serre gave a definition of EZI using the so-called TOR formula, and which we will see by the end of the lecture. Now, the point is that two given cycles may not always intersect properly, right? So, I mean, although I have not defined intersecting properly, but yeah, you can guess what it means. But anyway, so then we require what is called a moving lemma. So, in order to make sure that this really defines an intersection product on all of, let's say in the beginning Z star X, some sort of an operation, we need a result of the, or I mean, even in the Chow ring, we need a statement which says that given any two subvarieties, we can replace one or both by rational equivalences to obtain new two varieties which intersect properly. Okay, so if we show this, then the product will descend and will give a product on the Chow ring, and then the whole game is about showing that it is good and it does what it's expected to do. Okay, and so then the third step was to use a moving lemma. So by the end of today, I hope to, I mean, I'm giving two lectures. So by the end of the two lectures, I hope to write down a statement of the moving lemma and give geometric idea of how the proof works. And we should hopefully do the proof tomorrow. Okay, to show that, yeah. It is enough to define the intersection product on properly intersecting. Okay, so
speed breaker question.
Yes.
You don't mind speed breaker.
No, I don't mind them at all.
So after all, if they intersect properly, which I agree, there is a scheme intersection of and why not take it from down here?
Cycle, yes. So it is going to agree over at least over an algebraically closed field of characteristic 0. So yeah, but some more conditions may be required about. I mean, V and W themselves have to be nice. So this is going to come later in the lecture. Yeah. So and the answer is going to be in the TOR formula. Many times the answer given by intuition is concentrated in TOR 0, but then there are higher TORs which are necessary under certain conditions. So anyway, we'll see that. So yeah, so there are two moving lemmas. So let me state them right in the beginning. So just yeah, for the sake of safety, let K be an algebraically closed field of characteristic 0. I'll explain why I use the word safety. So there are two versions of this moving lemma. So one is called the basic moving lemma. Well, these are not the names given by me or, I mean the names which are, I mean people say this easy moving and hard moving and so on and so forth. I have picked up this terminology from a book called 3264 and all that. But anyway, I'm not following the treatment given in the book. Okay, so suppose that X is smooth projective. Okay, and then the first part says that given cycles of dimension R and X. Okay, so anyway, since I have not defined intersecting properly, let me not write the dimensions as yet. So given cycles on X intersect on X, yeah, there exists a cycle. So when I say cycle, everything is happening in Z, okay, Z of X. We are not gone modulo rational equivalence yet. So there exists a cycle alpha, which is alpha prime, which is rationally equivalent to alpha, and such that alpha prime and beta intersect properly. Okay, so this is the first thing. But the second thing, which is a bit more important now, okay, this would give you an intersection, an operation at the level of cycles. You would like to see that it descends to the through rational equivalence, and so then you will require that the class, okay, so of this cycle, which is the result of intersecting alpha prime and beta, whatever that means, which I have yet to define, in the Chow ring is independent of the choice of alpha prime. Okay, so this is what we need to show. So essentially this will involve showing that if you have a cycle which is rationally equivalent to 0 and intersecting beta properly, then the product also is rationally equivalent to 0 and so on. Okay, anyway, so this is the so-called basic moving lemma, and then of course the lemma tells you what the product of alpha and beta should be inside the Chow ring. It should be this class, right? So this gives you the product. Okay, but yeah, it does not say anything about the product, in the sense that it does not say if the product is nice, in the sense that it is functorial. Okay, so you would like, so if there is at least a flat map or any map, as you have seen, you can define pullbacks for any maps between schemes. So at least smooth schemes. So you would like to define, I mean, so there will be Chow rings and there will be a pullback map. You would like to know if this is a ring homomorphism under the product structure. But these things are not given by this moving lemma. Okay, so yeah. So one requires another one, so let's say strong moving lemma. Okay, so what does this say? So let Fy to X be a morphism of smooth projective varieties So what does the strong moving say? So given a cycle alpha on X, there exists a cycle. So right now, since I'm just introducing these, I'm not writing dimensions, in what dimensions they should lie and so on, but we will address these questions in hopefully 15 minutes. So there exists a cycle alpha prime, which is, say, of this form, as you decompose it into linear combination of cycles of irreducible closed subschemes. So which is rationally equivalent to A, rationally equivalent to alpha, such that if you take the inverse image of Zi, so this inside Y is generically reduced of the same codimension as Zi. So of course the codimension of F inverse of Zi is in Y and the codimension of Zi is in X, it's understood. Okay. And the second part actually says that if you take the class of the pullback cycle, which is so summation Ni F inverse of Zi, I think, anyway, there's a double, okay, so this will be in the Chow ring of Y. This is independent of alpha prime. Okay, so now let's,
Can you please tell me what you mean by
generically reduced meaning after you localize at the generic point.
There are several generic.
Yeah. So at you take every irreducible component and then take its generic point, and at all those generic points it should be reduced.
This codimension is also for every irreducible component.
Yes. Codimension is also for every irreducible component. Yes, good. Thank you. Okay, so now why is the strong moving lemma stronger than the basic moving lemma? So what is something extra that it gives? Yeah, of course, but I mean even when f, so okay, you would get the basic one if you take f to be inclusion, but even in that case it gives you something stronger. What is it that give you? No, but little bit more. So where does the intersection class live? That's what you should see. Okay, where does the intersection class live? So ultimately we want the intersection class living in the Chowring. Okay, but the strong moving, in case f is an inclusion, gives you a class on y, which is the subvariety. And using projection formula, etc., you can see that its push forward is going to be the intersection class. Okay, so it gives you something stronger. It does not just give you a class on x, it gives you a class on y, which pushes forward to the right class on x. Okay, so this is a slightly stronger statement. Okay, given that it's a stronger statement doesn't mean that it's true. So this has slightly muddy history. Okay, so now what is known? So
but you have not defined what is properly intersection.
That is going to come, as I said, in 15 minutes, so before 10 o'clock. So, yeah. Anyway, but first the statement should be, I mean, at least one should see where we are going. So then we can slowly work our way there. Okay, so what about basic A, the part A of the basic lemma? Okay, so this is already known. This is what is called Chow's moving lemma. This is correct. So the published proof appeared in 1956, but this was based on ideas of Severi in 1933. And also there was an alternate proof due to Samuel, who has done a lot of work about multiplicities, right, in 1956. Part B of the basic lemma is something that is, before I go to part B of the basic lemma, let me say that the part A of the strong moving lemma is a consequence of part A of the basic moving lemma. So that's easy, so that we will do, so let me just write it here. This implies A. So if time permits, we will do it, but otherwise you can take it as an exercise. It's not, hard. Now basic B, there's a proof due to Joel Roberts in 1972. So the precise reference is given in 11th chapter of Fulton. And there is a complete proof on the Stacks project. But I don't think it's the most ideal treatment, because it's not, Stacks project is not meant for linear reading. The proof is actually hidden in lots of, intricacies, which, anyway, but we will, so the aim is to give a proof of basic A and basic B here. Okay, so at least give a geometric outline of the whole proof. Okay, so now what about strong B? So this is the controversial part of the moving lemma. So there have been many proofs of this, but but none of them seem to work, and the gap has remained for 50 years, more than 50 years, with lots of great mathematicians looking at them. Okay, so there is some problem. So we don't really have this at this point. So this is where the big, this is something that justifies Fulton's book on intersection theory, because what he does is that he gives a completely different construction bypassing moving lemmas. what is quite amazing about the construction is that although, I mean, even after knowing that part B is correct, we don't have a direct proper proof. But after Fulton's theory, since he defines certain uniqueness statements for the, since he proves some uniqueness statements for the intersection product, the upshot is that the conclusion of strong moving is correct. Okay, so well, some part of it you have seen. I mean, you saw how to calculate multiplicities using Segre classes, and I think in Chetan's lectures he indicated how to connect that to the Hilbert polynomial. In this case, this treatment will be mainly driven by the definition of multiplicity through the Tor formula, and I think the commutative algebraists here know that the multiplicity given by this and multiplicity given by the Hilbert polynomial agree. So ultimately they are going to give rise to the same theories. But anyway, we will see that.
So the part is correct, it's just that
the proof is wrong. Or the direct proof has a, okay, there has been no convincing direct proof. Let's put it that way. Okay, but again, the fact that part B is correct took around 20-25 years to prove after it was stated. I think in the late 80s is when Fulton and McPherson wrote their theory, and yeah. Okay, so of course all these statements are dependent on geometry, and the proofs use that the base field is algebraically closed, which I believe can be reduced to, the assumption can be relaxed to infinite field, but at the cost of checking a lot of details. But still, I mean, well, there are direct proofs of moving lemmas, but anyway, yeah, let me come to it. But then why, okay, so there is, I just said that there is this nice theory of Fulton-McPherson. You have spent a long time studying it last week. Then why go into moving lemmas? Why not just give the Fulton-McPherson definition? So the reason is that there are plenty of theories in which the Fulton-McPherson machinery is not available. For example, higher Chow groups of block, where the Fulton-McPherson machinery is not available. Anyway, I'll make these comments later. Also, Chow groups of singular varieties, Chow groups with modulus. I mean, you have to do something using some version of moving lemmas which might work in your situation, because you don't have the general machinery of Fulton-McPherson. Okay, so that's why, and maybe in addition, heuristic significance. I mean, of course, there is a long history for this, and maybe it makes sense to learn it. Anyway, okay, so the Fulton-McPherson machinery is quite general in the sense that you can at least make definitions for an arbitrary smooth variety X over an arbitrary field. Then to check that they give you what you expect to give, you have to make several assumptions, such as the field is algebraically closed or varieties projective and so on and so forth. But anyway. Okay, so I'm going to, before Srinivas will require the existence of the intersection product on the Chow ring, and so I will give the Fulton-McPherson construction in a minute, since I believe what you did in the last week will be fresh in your minds. But before that, I'm going to give a definition, and that is, so okay, so one thing that was mentioned by Nitin yesterday in one of the, not yesterday, last week in one of the exercise, the discussion sessions, is that intersecting V and W inside X is equivalent to intersecting V cross W with the diagonal in X cross X. Okay, so this statement is quite important. The reason being that, so now V and W can be arbitrarily horrible, right? Given that, I mean, they are just sub-varieties, they need not be smooth and so on, or reduced or anything. But if your ambient variety is smooth, the inclusion of the diagonal is what is called a regular immersion. And so you are actually reducing the question of intersecting two arbitrary varieties to another one in which one of the embeddings is regular. And that is quite important, as we will see soon. Okay, so let me give the definition first. Okay, so I'm going to give these definitions because, well, okay, this is going to be a slight aside on regular embeddings and smoothness, but I'm giving it, yeah, just because, just to, well, you can look up these things and later if you are interested. Anyway, these are quite fundamental anyway. Anyway, so I don't want to get into scheme theoretic difficulties, so I will always assume that my schemes are locally Noetherian, but many of the things just work with locally of finite presentation. But anyway, I will, yeah. So, okay, so here's the definition of a regular embedding. So, a closed immersion so it's called a regular embedding of codimension D if every point of X has an affine neighborhood say U, which is spec of A in Y, such that the ideal defining X inside U is generated by a regular sequence of length D. So is everybody familiar with the notion of a regular sequence? Yes, everybody? It just means that it's a sequence of elements of the ring such that the first one is a non-zero divisor, then you go modulo the quotient, then the second one is a non-zero divisor in the quotient ring, then you can go modulo that, then the third one is a non-zero divisor in the quotient by the first two elements, and so on and so forth. Okay? And that when you go modulo, you don't exhaust everything. Okay, so yeah. Anyway, so yeah, so that's the, and then you take the, yeah, and if it has length D, then it's a regular sequence of length D. One has to be careful about when a permutation of regular sequences of a regular sequence is a regular sequence, and so on and so forth. And in nice cases, it doesn't matter when you're working in local situations and so on and so forth. But yeah, those results will not get into here. Anyway, most of the computations that we do will be local, in which things will be nice. Okay, so what's the importance of regular emergence? So it has something to do with the normal cone and the normal bundle, which you have seen in the last week. So so let I denote the ideal sheaf of X in Y. Okay, so regular, if the embedding is regular, what can you say about I? What can you say about I? Or what can you say about I modulo I square? It's locally free of rank equal to the codimension of the length of the regular sequence, right? So I modulo I square is locally free of rank D. Okay. Now, what is the normal bundle of X in Y? What does it correspond to? The dual of this sheaf, this locally free sheaf. Okay, so okay, let me write NXY. So this is the normal bundle. This corresponds to, that means its sheaf of sections is the I modulo I square dual. Okay. What about, so in other words, you can give this as the Grothendieck spec of the symmetric algebra on I modulo I square. Okay. Now there is another object that you have seen in the last week, which is the normal cone. So what's the definition of the normal cone? Does anybody remember the definition of the normal cone from the last week?
Take the direct sum of I mod I square and take this.
Okay. Now, is there a natural map from the symmetric algebra from I modulo I square to the direct sum of I to the n modulo I to the n plus 1? Yes? Yes, and what can you say about this map if I modulo I square is locally free? This is an isomorphism. Okay, and what does this mean? The normal bundle is isomorphic to the normal cone. Okay. Now, using the normal cone, you did a lot of things in your in the last week, right? So you defined Segre classes and so on and so forth. You made a lot of computations using them. Okay, so if you have a regular embedding, then the cone is nice. It's actually a vector bundle. The thing that we will use is that the Chow ring of the vector bundle is isomorphic to the Chow ring of the base. Okay, so this is going to be quite crucial. So this is where this helps. Okay, so the second thing that we need to address is the diagonal regular embedding. Okay, so is it? Yes, that requires a little bit of work, but actually the diagonal being a regular embedding is actually characterized as smoothness. Okay, so just for the sake of, yeah, I mean, although it's an aside, I'll give the definition so that you can go back and check the local calculation. So, okay, it's an aside. So what Supravat was saying was that if you have a closed immersion of two smooth varieties, then it's automatically regular. And this is true, but yeah, the diagonal being regular is slightly more basic, so which is why I'm giving this. Okay, so let me just define. So morphism of schemes from X to S is smooth. So I believe everybody has seen the definition of a smooth morphism, right? Yes or no? So can you tell me the definition? So there are three conditions. So one is F is locally of finite presentation, which you don't have to worry about if I assume locally Noetherian, but anyway. Then F should be flat. And what's the third condition? The main one? Yeah, but without talking about omega. Or which works over a non-algebraically closed field. Yeah, geometrically regular fibers. So that means for every geometric point, of S, the fiber is regular. Okay, so if for instance, if you are working over an algebraically closed field, then this is same as non-singular. Okay, but in general one has to be a little careful about these. Huh? No, when S is a field. When S is a field, when you are working over a field. Yeah. Smooth. Huh?
Meaning in your definition here, define all of it. F is smooth at a point of stress is also a phrase you may find.
Yes, but then I'll have to write more, so I will.
You can take X local.
Yeah, sure. So anyway, but now that they have said it, you know it. So I will take this opportunity to not write. Yes. So it's a local condition. Anyways, I will write a characterization which will involve the diagonal is it's a local characterization. So anyway, let's. Okay, so the following are equivalent. Okay, so the first one is that f is smooth. The second one is okay. So I'm writing the name, but I'll also write the condition. F is formally smooth. Okay, so what does this mean? So for every affine.
No, I think you have to be careful because you won't have to be a finite presentation. Formally smooth ones or
So let me assume let me assume Noetherian.
that's
Then, so I have to.
see, you might have infinite field extension characteristic 0
Yes.
and it's not there.
Yes.
But it's not smooth. It's formally smooth.
Yes. So I should assume F to be of finite type, morphism of finite type.
Your B, you are and finite. Formally smooth.
Yeah. What?
Nothing to do with only adjective schemes, where schemes finite
In well, I did not make any such assumptions, right? In the beginning, I only said locally Noetherian. No, what about Q? See, all the problems will be demonstrated if you look at Q bar over Q. So, well, anyway. So, anyway, let's not do too much of a digression. But anyway, so for every affine S scheme T and a subscheme T naught of T defined by a nilpotent ideal so any T naught valued point of X can be lifted to a T valued point of X. That's the condition. So in other words, the map xt to xt naught is surjective. Okay, so that's what formally smooth means. And then the third condition is that the diagonal is a regular embedding. Okay, so the diagonal being regular embedding is already a characterization of smoothness, but yeah, anyway, so that's given when you start with X smooth. Okay, so the upshot is that, so now that you have reduced the intersection of V and W to be that of V cross W and the diagonal, one of them is a regular embedding. So it makes sense to, so its normal bundle is nice. It,
Excuse me for nitpicking.
yeah.
Perhaps you have to move this F is of local finite.
I think in the upstairs, because yeah, yes. So that's why I was this wrong. So let F X to S be of finite type. Okay. Yeah. No. Thanks for this. What? I don't think you need separated. Yeah, so let's search.
Smooth are not separated.
Yeah, smooth.
An affine line with double origin is smooth.
Yeah.
You have precise parts, right? One
Why?
has- Because take S to be take
That the to make sense of this as an embedding, this is closed. The diagonal is closed is a problem. So okay, let's assume separated. Okay. Okay, so so now that we know that, okay, so now let's get back to work. So, okay, so now what do I want to do? So I think I'm already falling behind. But anyway, so what I should do is I should first define the intersection product a la Fulton-McPherson so that that part is taken care of, and then I can.
Supposed to happen at 10 o'clock?
I was supposed to define properly intersecting. So I am behind by 5 to 10 minutes. So let me change the plan, and then let me give you the Fulton-McPherson intersection product first, and then let's go on. Okay, so what's the setup? You have a closed immersion. Oh, okay, yeah. Let me assume regular embedding. And F from V to Y, any morphism. Okay, so now define W to be the fiber product of this. So I and F. Okay. So the so now you have the cone of X in Y and the cone of W in V. Okay. So W is defined as the pullback. So now what do you know? Since since I is a regular embedding, these two are vector bundles, right? So this so these both, I mean CWV and CXY are vector bundles. So now
The second square Cartesian.
this is Cartesian.
No, second square.
This need not be.
Arrows are in the wrong direction.
No, this is the bundle over this.
The bundle.
Yeah, this is not this is not Cartesian.
That way.
So let me point out that this is not Cartesian. Only this one W is defined to be the pullback. Okay, so this is Cartesian by definition. So not necessarily Cartesian is what I should say, but anyway. Well, so now okay, so let me call this map G. Yeah, okay, so so let S from so W to, so take the pullback of the normal bundle. So the normal bundle is over here, take its pullback over here and look at the zero section of the normal bundle. Okay, and now define, okay, be the zero section. And now define the intersection product to be, so now last week you defined a morphism called Gisin map, right, for these kind of for closed embeddings. So you apply the Gisin to the fundamental class of the cone above. Okay, so what does so where does this lie? So this lies inside the chow ring of the cone, but since this is a vector bundle, this is isomorphic to the chow ring of Y of W. Okay, so now you have got so this is the Gisin map. So this defines an intersection product. Okay, so this will give you the product structure on the chow ring. So I think in Srinivas's lectures in the first few, I think he's only going to require that there is a product on the chow ring. Okay, so now you know the definition, but then of course there are lots of compatibilities to be proved, functorialities to be proved, and all that, and this is done in chapters 6 to 8 of Fulton.
The name refine Gisin or something.
That I will not yet. So I will for lecture number 4 of mine.
The map from W to V, that may not be regular embedding. X to Y is a regular embedding. So why that is a CW is not a vector, may not be
Base changes.
No, it's a base change, no? Base change of, yeah. Base change of regular embedding is a regular embedding. So anyway, that has to be checked. So anyway, so the plan is as follows. So today, the whole of today is going to be devoted to studying proper intersections, what it means to intersect, what it means to say that two varieties intersect properly. In that case, what is the intersection multiplicity, how to calculate it, and then of course this statement that the diagonal is a regular embedding, and then you have to, I mean, intersecting V and W is the same as intersecting V cross W is a diagonal. This approach is also important in the classical setting. So we will see that in the classical setting today, and then I will end today's second lecture with hopefully the statement and the geometric idea behind the proof of moving lemma. In tomorrow's first lecture, we will prove the moving lemma, or at least give an outline of the whole proof. And then in the last lecture, we will look at the Fulton-McPherson theory, and I will give you an overview of chapters 6 to 8 in Fulton. Okay, so that's the plan for these 4 lectures. Okay, so now, let's get back to, so this was all to just justify that this is a really key property which allows you to do certain things. So this is not going to be applied just directly, right? So you will take the diagonal here, and you will take V cross W here, and this Y will be X cross X. That's what will give you the intersection part. Okay, so now let's move ahead and get back on track. Okay, there is another concept of an LCI morphism which any of us might require. So let me define it right now or later. Okay, maybe later. Let's not worry about it right now. Okay, so let's get back to intersecting things properly. Okay, so let f from x to y. Yes?
So we don't require the V2Y morphism to be.
Don't require any properties on V2y.
So I mean, you said that the base change of the regular embedding would be regular. Don't we require the non-zero divisors to go to non-zero divisors?
Yeah, right. So actually, thanks for catching me. So, okay. So, well, this construction as of now makes sense only when this is, nice. But, there will be something called refined Gisin map, which will be defined, which I will define in the 4th lecture. Then it will be completely defined. But anyway. He's saying that how to make sure that in the pullback of a regular embedding is a regular embedding. You might require some conditions on to say that this is a bundle. But actually, you can do without it, because you can just push down the class over here and then push it down over X, and then, but maybe, I don't know. No, but anyway, let's be careful. Let's not. It's probably required. So anyway, let's do that later. But this is the basic kind of gist of the construction. Yeah, so let X be a morphism of varieties. Okay, so if F is a regular, okay, let me just write it. Be a regular embedding of codimension C. So if Z is a subvariety of Y of dimension D, then, so what's the dimension? What can you say about the dimension of every irreducible component of F inverse Z? Yeah, what can you say about the dimension? Z is of dimension D. F is a regular embedding, so locally it's given by a regular sequence. What happens when you cut by a regular sequence? The dimension you can by 1, right? Or at least 1. So yes. So what can you say about the?
If it's a D-length regular sequence, it drops by D.
It's of length C, so it should drop by at least C, right? So at most C. Sorry. So this is greater than or equal to D minus C. Yeah. Anyway, so this is an easy statement. I leave it to you as an exercise. Okay, so in the exercise, if you, this is quite easy, but if you don't know how to do this, we can discuss during the discussion. Okay, so yeah. So what can you say? So as we have been saying, so let VW inside X be closed subvarieties of dimensions R and S. Okay, so now we have just seen that the intersection of V and W is just the inverse image of V cross W under the diagonal. So what can you say about every irreducible dimension of every irreducible component of V intersection W? It has to be at least just apply the thing above, right? So what's it greater than? R plus S minus the dimension of X, right? Okay, so here's the definition. Okay, so of proper intersection. So we say that V and W intersect properly if every irreducible component of V intersection W dimension. So now I'm just going to write. So I want to say exactly R plus S minus dimension of D, but I also want to include the case where the intersection might be empty. So I'll just write less than R plus S minus. Yeah. Okay. I'll put it. Yeah. Yeah. So then it will be minus. Yeah.
No, every irreducible component. Show me one which doesn't have.
Yeah. Okay. Yeah. That's correct. Yeah. Okay. So now equal. I want this to be equal.
Yeah, only asking for irreducible. No, you don't care about embedded components, etc.
No, I will be interested in the cycle giving associated to V intersection W. So the irreducible components are the only ones that matter, and the multiplicities. So it will be taken care of. Yeah. So okay. Anyway, so now just a definition about cycles. So two cycles. So alpha. And so let's now, so of dimension R and beta of dimension S intersect properly if Vi and Wj intersect properly for all ij. Okay, so now we are going to, for properly intersecting subvarieties, we are going to define the cycle v dot w. So where should it? So in which dimension does the cycle lie? R plus s minus the dimension of x, right? Okay, so define. Okay, so for v and w intersecting properly, define v dot w to be E z z. So where this sum is over irreducible components of v intersection w, and where does this lie? Z of r plus s minus dimension of x, right? So now I have to define this cycle. So I have to give a definition of Ez. Huh? What?
Class of V and class of W.
Yes. I mean class of V and class of W, but I'm just just for simplicity I am so I'm actually taking sub varieties here. So okay. So the notation is from here. So V and W are closed sub varieties of dimension R and S. Yeah. So you have to talk about closed subschemes, and then one has to worry about multiplicities and so on. But anyway, from this you can do everything linearly. So yeah, and I'm just forgetting the square bracket notation just for simplicity. Okay, so now to define this, I have to define Ez, right? So, and as I said before, this Ez is actually dependent on 4 things. So it actually depends upon x, v, w, and z. Okay, so this by definition is the famous Serre-Tor formula. So I'll first write it and then say something about it. So this is the alternate sum of the tors, of the lengths of the tors. So length of, okay, so you have fixed an irreducible component of V intersection W, right? So you can look at the local ring OXZ, so which is localization of X at the generic point of Z. Okay, and now you can look at the ith tor as OXZ modules of OVZ and OWZ. Okay. Okay, so this might look little scary in the beginning, but in lots of nice situations, it happens that only the tor 0 contributes and the higher tors are not there. So what is tor 0 in this case? So what is it? So tor 0 OXZ, OVZ, OWZ. Okay, so what is this? So okay, so just for simplicity, call this A, and then this will be like A modulo I, this will be like A modulo J, right? V and W are subvarieties. So what is this then? A mod I tensor A mod J. What is it? This is A mod I plus J, right? What is this? The localization of the intersection at the generic point, right? I plus J is the ideal of the intersection. So this is basically O V intersection W Z. Okay, so this is the answer given by intuition, right?
One basic algebraic point.
Yeah.
Those are finite length. Those tors are finite length because both of those are etc.
etc. Yeah. You have to justify that. Yeah, the lengths are finite and so on. Yes. So yeah. So okay. So when will this thing happen? So do commutative algebraists know some conditions when all higher tors vanish? Or
calling a flat
That's so some condition intrinsic on V and W. Cohen-Macaulay. If these two rings are Cohen-Macaulay, then the Tor will vanish. But anyway, so it happens that if you look at Bezout's theorem and these kind of examples, the usual examples that you write usually have this condition inbuilt. If your varieties are already nice, but it need not always happen. Okay, anyway, so I will.
The intersection property is going to be dimensional. This one equals to that.
No, that was just to take care of empty, as he pointed out. It was I want equal to. Okay, so okay, so now okay, so now given this definition, you can easily by linearity extend it to all cycles, right? So you have a definition of intersection product for cycles. Okay, so I will not write that down. That's clear, right? So extend linearly to cycles. Okay, so now so I'll just write here. Linearly to properly intersecting cycles. Okay, so now, so there is also a notion of, so first thing that one has to check is if things given by intuition are really correct or not. Okay, so sometimes two subvarieties V and W intersect transversely. In this case, we should be able to check that the intersection multiplicity given by this kind of a formula is indeed 1. Okay, so what is the definition of intersecting transversely? Can somebody tell me? So when do you say that V and W intersect transversely? Intrinsically, in terms of lengths, maybe. What? So too many voices, just one person, yeah. Or in terms of length, has length 1 over? No, not itself. In X, you want the varieties to be intersecting transversely in an ambient variety, right? So the definition should have reference to the ambient variety as well.
Dimension of V intersection W, that is not the codimension. First of all, the condition on V and W. Intersect transversely. What can we say about V and W? There is shared common. What is that? That's just saying there is a parabola intersecting the x-axis
Transversely. So?
Double line.
Yeah.
Transversal to the origin. The first thing is that V and W should be smooth pencils. Otherwise, V and W should be smooth pencils. At that point.
Yes, but that will come as a consequence. So yes, that is going to happen. But
so that means you should have a sequence for V, you should have a sequence for W.
So this will happen. This will actually happen if you just assume that. So the definition in terms of length, if you assume that to be 1, it will automatically happen that V and W are smooth at the point. So this is exactly what we are going to prove.
So why not just the intersection to the points?
That is also fine. Yeah, that is also fine. Then you can say intersecting properly at yes, but I want to talk about intersecting properly, intersecting transversely along an irreducible component of the intersection. So I have to be but that is the definition. So at the generic point of that component, that's the definition. So let me write it down. Okay, so. Okay, so we say that intersect transversely along an irreducible component Z of V intersection W if length as OXZ module of OV intersection WZ is 1. So if you take the generic point of that intersection of that irreducible component and look at the length of V intersection W at that point, it should have length 1. Okay, so this is what we are going to prove soon, or maybe in the next lecture, is this. Okay, so let X be a smooth variety over K, and let VW be closed subvarieties of X intersecting properly. Yeah. Suppose V and W intersect transversally along an irreducible component Z of V intersection Y. So then two things. So the first, V intersection W. So then the intersection multiplicity at Z is 1, and V and W are smooth at the generic point of Z.
But actually, all higher codes are zero, which is counter than
What?
all higher codes are zero, which is counter than A. A is not your statement A.
But I mean, that's not automatically given because we have not assumed.
This statement
Higher tors are,
zero there. It's not just the answer.
yes. So yeah, that's true. Well, okay, yeah, we'll see that in the proof. Okay, and the second one is exactly what Kapil had pointed out, right? So the parabola and x-axis, they are not intersecting transversally because at the intersection point, it's the varieties are they smooth or not? No, right? Because the intersection as a scheme is a double. It's a double point. So, but if you move the x-axis a little bit, then the intersection is proper. Okay, so this is what we will prove perhaps in the next lecture because there are only 15 minutes, or I can do it now, but I need some commutative algebra preliminaries, so which I am going to introduce. So in particular, I will require a way to compute TOR, and a way to compute TOR is using a resolution of one of the modules. So modules are going to be of the form A mod I, A mod J. What's a canonical way of getting such a resolution? The Koszul complex. Okay, so let me just, is everybody familiar with the Koszul complex? Some of you are, but anyway, I will introduce it. Yeah, but we have not proved B first. Yeah, it does imply. B implies A, so maybe I should write it. In fact, the proof will first prove B, but anyway, yeah, and so A will be a corollary higher. What?
What is the difference from smooth and the generic point?
Localization at that point is a regular local ring. Okay, so note that the whole of V and W need not be smooth. Only localizations at the generic point are smooth, are regular. Okay, so yeah, that's important to know. But anyway, yeah, so let's just do a recall. Okay, so let A be a Noetherian ring and let X belong to A. At this point, no condition. Okay, so soon X will be a non-zero divisor. But okay, so now what's the Koszul complex on one element? Anybody? It's a two-term complex, right? Yeah, so you take multiplication by X and 0. And so if you have a sequence of elements, okay. So then the Koszul complex on this sequence is, so how is it defined? It's the tensor product of all this singular, of this Koszul complexes on one elements. Okay, so this is called cheating, but anyway. Okay, so what's the tensor? Yeah, I'm going to say it orally. So what is the definition of a tensor product of two complexes? So by you have to take a double complex, you have to know how the differentials are defined, and then you have to take the total complex of that double complex, which is in which you take sums, direct sums of all the diagonals, and then you get a natural differential between them. So is everybody familiar with this? Okay, so that's what you have to do. Okay, anyway, so what is the ith term of the Koszul complex? So it's going to be a complex of free modules, right? Because all the terms are A, so it's going to be tensor product of, or I mean direct sum of and tensor products of A's. Okay, so it's going to be a free A module. What's the rank? N choose I, right? Okay, so now to get nice properties, you have to assume that the sequence is nice. Okay, so in what?
You want to write like the index number, you want to index it by choosing I out of X.
Yes, that's what, but I will never use, I will only use the fact that the Koszul complex is a resolution. I will not do any explicit computation with the Koszul complex. So right now I will not write it that way. So yeah, this was just to tell what the ith term looks like. Okay, so there is also, I mean, we will require it for A mod I and so on and so forth. So for any A module M, so define the Koszul complex on M to be just the tensor of this Koszul complex. Okay, and of course you can look at the homology of the Koszul complex. Well, you can grade the Koszul complex homologically as well as cohomologically, blah blah blah, and then, well, your notations have to be proper, but anyway, I'll use the homological grading. Okay, so what are the facts about Koszul homology? So looking at this homology and looking at where it vanishes gives you a lot of information about how the sequence X is like. Okay, and yeah, so let me quickly recall the facts, which I will not prove. So first says that the ideal, so now this complex is given by a sequence, right? So if you look at the ideal generated by these x1 to xn, this annihilates the homology. Okay. Okay. So let me call this I. So let's assume that I of m is not m, and now I want to read something out of the first term which is non-zero. First homology which is non-zero.
But why not H0 first?
So you want me to say that H0 is the quotient of this by the ideal? Yeah. So yeah. So actually, if you just look at how so you can easily see what the first differential is going to be, right? It's going to be, yeah, it is going to be the given by a to the n to a given by all the different factors given. So summation xi ei is going to be the map, right? So the zeroth fact would be, so this will be, okay. Yeah, so now, okay, so if you assume I am not equal to m, and if you look at you go on looking at the Koszul homology, the homology of this Koszul complex, and you see the first one which is not zero. What can you say about that? Some commutative algebraists maybe? This may not be common knowledge, but in terms of depth, yes, but what does that? Yeah, depth I am, but what does that tell you? So what is depth I am equal to? The minimum of I such that which homology one? Okay, I think I have to be careful because of the homological notation. I am generally used to doing things in homological notation. Okay. Yeah, okay, but the things that, okay, I mean, this is not really going to be required unless, yeah, you assume that things are Cohen-Macaulay, in which case depth equals dimension, and then lots of things happen. But anyway, so the thing that we will be mainly interested in is what happens when X is a regular sequence. Okay, so if X is an M regular sequence, then what can you say? The homology vanishes. In positive degrees, yes. Greater than 0. Okay, not at, because at 0 you know what it is up there. Okay, and so partial converse is true if A is local. Okay, so if A is local and X is a sequence in M, the maximal ideal, such that the first Koszul homology is 0, then this implies that X is a regular sequence in the maximal ideal. Okay, yeah, so now we are ready to prove this proposition, but since there are only 5 minutes remaining, I will not finish the proof, so let me just start from here in the next lecture. Okay, and so are there any questions?
All this derivative method that we are working about,
Not really. Yeah, up to now, no. Up to now, no. And actually, V cross W will not be a variety even over a base field. K equal to K bar has not, algebraic closure has not played a role up to now. Algebraically closed plays a role only in the proof of moving lemma.
I'm saying there's not even a base field in what it is.
Yeah.
No, but you define the intersection value to be del inverse V plus W, right? But del inverse is defined only on varieties. If K is not algebraic.
No, you can take the inverse image of a subscheme And then you have to go through the Fulton definition, right? You have to look at irreducible components, look at multiplicities, and define a cycle. So everything makes sense up to now. By the way, just this easy point which you have seen many times by now, V cross W need not be a variety, right? You know that. For even if V and W are varieties. What is the simple example? Over a non-algebraically closed field. C tensor C over R. Okay, spec C over spec R is a variety because it's given by Rx modulo x square plus 1. But C tensor C is C cross C.
And give one more example to show multiplication. F P square over
Yeah, F, okay, but now Nitin has already given it. So.
not F P square.
Fp t to the power 1 over 2, Fpt, yes.
C to R example generalized training. Yeah, but I'm saying where
Multiplicity has to be, yeah. So, yeah.
Any finite pure algebra
Yeah.
it's no more true.
Yeah. Okay, so this, yeah. Okay, so I think this is a good point to stop. We will continue with the proof of this in the next lecture.